Sorry, please. Sorry for the interruption. It was due to technical reasons. So we look at apparent weight in a fluid. Apparent in a fluid. Let me check. Attendance. Nobody's viewing. Okay. So if you place a stone on a scale that is calibrated to measure weight, then the reading on the scale is the stone's weight. That is, you get, assuming everything is correct, no air resistance or anything, what you get is the weight of stone. However, if it is underwater, that is, if you allow the stone to be lowered from that scale, string, water, there will be an upward buoyant force on the stone. Thereby, the reading of what we now as the weight will decrease apparent weight. And this has something to do with the actual weight of the body and the buoyant force on the body. Being equal to the actual weight minus the buoyant force. Can we get that? The apparent weight that we can read is the something is up. Okay. Go back to it. Okay. So we want to look at floating buoyancy and density. As you can see in the figure below, the height of that figure is capital H, but the small h is the height by which it is inside the fluid. So, by flotation, we require that the upward buoyant force on the block match the downward gravitational force on the block. Also, the buoyant force is equal to the weight of the fluid displaced by the submerged portion of the block. We also find that the upward buoyant force has magnitude, which we can write as that. If you remember, the buoyant force is something about the weight of the object. And so if you look at that weight, that's mass times the acceleration due to gravity. And mass has something to do with the density and volume. And then again, you can go ahead to write something about volume in terms of the length, width, and the height. The length, width, and the height. So that's the expression that we have above there. Then the gravitational force also, we can write it also as the mass of that object and the acceleration due to gravity. So similarly, we can write it like that. So the floating block is stationary, so it's not moving. So normally, if you write the net, the force should be equal to mass times the acceleration. But since there is no acceleration on that vertical part, and of course, it's static anyway, whether vertical or even horizontal component. So we can write Newton's second law by just saying the buoyant force and the weight is essentially zero. And we can write that as what we have in that next line. So that really the density of the block, the density of water, everything comes to play. It just, as if you cancel the width, it's still the same width, and the length has been submerged. It's only the height difference on that left hand side. And that height also on the first term and the second term. So what at play is the density and the height that we saw in that expression. So if you look at that, what we just have is 4 centimeters. That's the depth h by which the block submerged. That's the depth h by which block has been submerged. If you want to also find the magnitude of its acceleration when the block is fully submerged and then released, is submerged and then released. So if it is released, you know there's a motion. So in that wise, you don't have the difference between the two being equal to 0, or rather, you now have m and a. So what we survive also, we just tell us that the acceleration is 4.9 meters per second squared. We are taking note of all that. So let's look at the fluids in motion. The fluids in motion. But please let us see that we understand this sample. This sample is very important. Sample problem. Sample problem on slide 14. Very, very essential. So we look at solution about the fluids in motion. Can we have what we call real fluids? Real fluid theoretically may be difficult to be discussed. What we can discuss is what we call the ideal fluid, because it is simpler to handle mathematically and yet able to get results. You know, if you have done just ordinary binomial theorem, if you want to do 1 plus 0.02, you want to do binomial theorem that when it's raised maybe to an index n, or n is 2, you know, get first term, second term, third term, you can stop at all term. But if you to order higher terms, the values you get becomes very exact or nearing the exact solution. But for theoretical consideration, by the time you are having first term, second term, and third term, good. At least we're able to describe the motion. So, by the time you are getting to those second, third term, but when you want to get to that, that's the difference between free fluids and ideal fluids. Okay, fluid and ideal fluid. So ideal fluid is sufficient enough for us to theoretically consider fluid and fluids in motion. So we want to look at some terms that will be very useful. This course or this topic actually becomes something very handy for many of us that because of your program, maybe at your part 2 or 3, or even higher levels, you still come across fluid mechanics. This will form the basis from what you have done at low level and what you are doing now. Actually, will form the basis upon which you're able to discuss fluid mechanics very well. And for those who in the area of looking at thermodynamics, heat flow, heat transfer, you also need to have some of these topics, some of these terminologies in your mind, so that when you are doing those courses, you're able to understand exactly what we are talking about. Say heat flow, we'll be talking about gases or even fluid generally, or fluid mechanics as relevant to many of us that will be maybe in food technology, those who will be in even mechanics, those who will be in mechanical engineering, and many other topics that find relevance to discussing fluids. So what do you mean by steady flow? A steady or laminar flow. Laminar, that is no disruption. The fluid is just moving gently. The velocity of moving fluid at any fixed point does not change with time. It does not change with time. That's the case if you look at a gently moving stream or a river. Then you say gently moving. By the time you put maybe an obstacle in the stream flow, you have created a kind of a barrier. You allow the fluid to be agitated at that point. But if the fluid, there's no obstruction, the fluid just moving, easily. You see, that's a laminar flow or a steady flow. So gentle flow of water near the center of a stream is steady. The flow in the chain of rapids is not. Okay? We had something making it to be rapid. And we are not talking of a steady flow. For the sake of your exam, you must understand those terminologies. Your test and exam, you must understand them. So we assume, as fluids that our ideal flow is incompressible. Incompressible is talking about the density. Okay? And talking about that the density has a constant uniform value. Incompressible flow. Okay? For an ideal fluid, the density has constant uniform value. Okay? In the steady flow, we are talking of the velocity is constant. Steady flow, velocity is constant. That's a summary. Incompressible flow, we are saying the density is constant and has a uniform value. Then the next one is non-viscous flow. Roughly speaking, the viscosity of a fluid is a measure of how resistive the fluid is to flow. Okay? Non-viscous. From our level or from the physics we have done before now, when we talk of viscosity, we are talking of friction in between molecules of a fluid. Okay? But what I'm saying for ideal fluid is non-viscous. Thick honey is more resistive to flow than water. And so honey is said to be more viscous than water. Viscosity is the fluid analogy of friction between solids. So an ideal fluid is non-viscous, or we undergoes non-viscous flow. Irrotational flow. We also assume that the flow is irrotational. And this property, if you look at a tiny grain of dust as it moves in a fluid, though this test body may or may not move in a circular path, in irrotational flow, the test body will rotate about an axis through its own center of mass. Okay? For a loose analogy, the motion of a Ferris wheel is rotational. That is, on a wheel, it is rotational. That of his passenger, the passenger that is seated, is irrotational. Okay? So I like this figure, and for those of us that will be looking at combustion theory, this figure is very, very important. The one on the right, and then the one on the left, talking about combustion theory, and then the one on the right, talking about the way fluid will move. You know, I told you, if there is no obstacle, you can see the obstacle black in the right side. So because of that obstacle, instead of the fluid to move smoothly, just as it was moving at the initial point, on getting to that obstacle, there is a kind of rapid movement. And that rapid movement is trying to circumvent that obstacle. So there will be a delay, and all the molecules will move round about that object. And that is the case also with solar wind that comes from the sun. On getting to the earth, it describes something similar to what we have here. And so we have what we call the bow shock. The bow shock is somewhere there. At this point at which, they start to move, trying to move around that object is obstructing the flow of fluid. So they are trying to move around. So many of them will move around. Only tiny part of them will still stay and be close to that object. And if they have the opportunity, depending on the nature of the object, some of them wants to pass through that object. And that's why we still have some of solar energetic particles coming from the sun getting to the earth. Thank God that there is that obstruction. And then we have to pass, from that side. Then in case of this, you can see that's a cigarette light, burning set flame. At the point close to the flame, you can see that the fluid is moving gently. But as it is moving away, the flow becomes blown up. Mathematically, you can actually describe that motion. Those in mathematics and those who will be looking at combustion, as in the case of the rocket, you come to know how to write a mathematical expression to actually describe such a motion. Very interesting, you mean? Because in our ability to describe it, we'll be able to do a lot of prediction about flow and have a great deal on the motion of our object of interest. So we can see that figure shows a transition from steady flow to non-steady flow for a rising stream of smoke from a cigarette light. Then we should know that each bit of a tracer, another figure by your right, follows a streamline. You can see that the streamline, even in the case of the flow around the cylinder that we have on our right, that none of them is crossing themselves. They won't cross. They only want to attempt to cross themselves when there's an obstruction. So we can theoretically draw what we call a streamline, which we have with that figure right, the second figure on your right. A streamline, which is the path that a tiny element of the fluid will take as the fluid flows. A fluid element traces out a streamline as it moves. The velocity vector of the element is tangent, you can see, to the streamline at every point. So these are theoretical bases upon which we can actually describe the flow of fluid, whether in the case of combustion, or in the case of a flowing solar wind or any other thing that flows. So the velocity of a particle is always tangent to the path taken by the particle. Here, the particle is a fluid element, and its velocity to a streamline. For this reason, two streamlines can never intersect. I hope you are taking note of all of these theoretical considerations when we want to talk about fluid flow. Very, very important. You know, I told you, in setting equation, up to set 10, you can be sure 4 of them will be something theoretical. And if I'm setting 40, it means 16 will be theoretical. Okay? So it's very good for you to know some of these theoretical statements, because they are statements of facts that can help us to understand any physical principle, and in this case, fluid motion. Then, if they did, then an element arrive at the intersection, we have two different velocities simultaneous and impossibility. It's impossible. That is, if two streamlines can intersect, imagine, you say the flow, there's a velocity vector that is tangent to it. So imagine that if you now have two streamlines intersecting themselves, okay, what happens? There will be two different simultaneous velocity. Imagine a fluid flowing and you have different velocity. I know that's no longer, that will be a case where we are talking about maybe turbulence. Okay, that's now a turbulent flow, and that's not for this class now. So in the equation of continuity, you know, is something deriving from theoretical consideration. You can increase the speed of the water emerging from a garden hose by partially closing the hose opening. Let's take our attendance, please. We are going to take 2 attendance. Let's take our attendance. We take our attendance now. Attendance 1. ML S 7H. Attendance 1 now. ML S 7H. MLS 7H. That's attendance 1. I hope you have taken that. Attendance 1. MLS 7H. That's attendance 1. MLS 7H. Because of our time, we'll take attendance 2 immediately. Our time is almost up. Our time is up already. Our time is up. Attendance 2 now. Let's take attendance 2. Attendance 2. Z73 NL. Z73 NL. Attendance 2. Attendance 2. Z73 NL. So let's go back to our slides. In closing, we've discussed today fluid flow and ideal fluids in motion. We're able to look at steady flow, constant velocity, incompressible flow, having constant density, non-viscous flow, in which case a fluid in which the friction between molecules is 0, and then we'll look at irrotational flow. And then we're able to discuss and actually understand what we mean by streamline. Okay? Streamline is a bit of is the part that a tiny element of the fluid will take as the fluid flow. That's what we call streamline. Is the part that a tiny element of the fluid will take as a fluid flow. And of course, the velocity vector of the elements is actually tangent to the streamline at every point. These are very important points. And of course, two streamlines in an ideal flow can never intersect. Because if they do, we'll be talking of two different velocities simultaneous. And that is impossible. That's not possible. Okay? And of course, today also, we were able to talk about apparent weight being the actual weight minus the buoyant force. That is, if I have a string and I attach a weight to it. If I have a scale by that string, I'll be able to measure, say, spring balance. I'll be able to measure the weight of that object by reading what is there. But if I lower that object in a fluid, say water, for example, the apparent weight, because it will be real weight now, okay? The apparent weight will be equal to the real weight minus buoyant force, because there's a buoyant force that will push it up. Okay, so I should take note of that. So that's what we're able to get in place also. And again, we're able to look at Archimedes' principle and the principle of flotation, how they are related. So that's what we're able to today. Let's take the last attendance code. The last attendance code. The last attendance code. BU 4. Let me take that again. BU 4. BU 4. That's the third attendance code. That's the third attendance code. So we have taken 3 attendance in the course of this lecture. Actually, our stopping time should be 11. But for today being Friday, we want to stop earlier than the time. So please, any question? Let me see if you have any question. Any question? Any question? Any question? So, if there are no questions, no. I can't see. There's a question come up here. So, see the question. This thing is covering it. How do I move? Do I just do like this? Like this? No, confirm. We'll give that a question. Okay. So, sorry. Okay. So I should repeat the first code. Sorry, I can see that. The first code is MLS 7H. First code, MLS 7H. That's the first code. Second code, Z73NL. Third code, BUAL4. Let me take that again. First code now, MLS 7H. 7H, H for house. MLS 7H. Code 2, attendance number 2, Z73NL. Z73NL. Code number 3, BUAL4. BUAL4. Code 1, MLS 7H. Code 2, Z73NL. Code 3, BUAL4. So I think with that, we have come to the end of the class today. Hopefully we'll meet again on Monday. Sorry for the interruptions that we have today, and I hope Monday will be better. So thank you. Meet you on Monday, God willing. Thank you. Thank you, sir.